Good day to all of you. So, in the last two chapters of this operating systems lecture series, we'll be dealing with case studies about the specific operating system, of course, that has been existing and been used by many of the users. So, one of them is the Linux system. This is the most popular open source operating system. So, of course, Linux has many distributions. So, for this chapter, we will know about the details of how does the Linux system as an operating system works and its distinct characteristics in relation to other operating systems. So, let's start our lesson. So, chapter 20 is all about, again, the Linux system. So, the contents of chapter 20 is we have the Linux history, design principles, kernel modules, process management, scheduling, memory management, file systems, input and output, interprocess communication, network structure, and security. So these are the following objectives for this chapter: to explore the history of the Unix operating system from which Linux is derived and the principles upon which Linux's design is based. Next is to examine the Linux process model and illustrate how Linux schedules, processes, and provides inter-process communication. Next is to look at memory management in Linux and to explore how Linux implements file systems and manages I/O devices. So for the history of the Linux operating system, Linux is a modern, free operating system based on Unix standards. It was first developed as a small but self-contained kernel in 1991 by Linus Torvalds, with the major design goal of Unix compatibility, released as open source. Its history has been one of collaboration by many users from all around the world, corresponding almost exclusively over the internet. So the collaboration is more of because it's a community. So if there is a change with regards to the source code and implementation of Linux, the collaboration is almost done in the internet. And then it has been designed to run efficiently and reliably on common PC hardware, but also runs on a variety of other platforms. As I can remember when I use Linux when I'm trying to terminate a program, unlike Windows, in which for me, in my opinion, it's relatively slower than Linux. If you really terminate, then it will in an instant it will terminate the program in execution. And then the core Linux operating system kernel is entirely original, but it can run much existing free Unix software, resulting in an entire Unix compatible operating system free from proprietary code. And then the Linux system has many varying Linux distribution. As I've said, the other term for distribution is Linux flavors, including the kernel applications and management tools. So for the Philippines, but it's discontinued by the Department of Science and Technology, they have implemented Bayanihan Linux, but of course, maybe because of funding. So unfortunately, our own Philippine-owned copy of Linux is being discontinued. Okay, next is we have the Linux kernel. So the version 0.01 in last May 1991 had no networking, ran only on 8386 compatible Intel processors and on PC hardware, had extremely limited device, drive support, and supported only the Minix file system. And then on after 3 years, March 1994, we have Linux 1.0. So by as you can see with the versions, it means that it really has a major revisions because from version 0 it became 1. So included these new features. So the first version, the 1.0 version of Linux, is support for Unix standard TCP/IP networking protocols, BSD, or BSD means Berkeley Software Distribution. So it's another type of Linux. So BSD compatible socket interface for networking programming. And then device driver support for running IP over an Ethernet. Enhanced file system. Support for a range of SCSI controllers for high performance disk access. and extra hardware support. Then next is we have, after a year, March 1995, we have version 1.2. So as we can see, it's still version 1, but with a minor change. So that's what what's the idea of versioning. If the whole number changes from 1 to 3, it means it's a major revision. While the same version, but the change is after the dot, meaning it has revisions, but not as significant as from version 1 to version 2. So the version 1.2 was the final PC only Linux kernel. So for Linux, kernels with odd version numbers are development kernels, meaning these development kernels can be used by the developers who want to experiment with Linux operating system. And those with even numbers are production kernels, meaning these versions of Linux kernels are used exactly for work. They are not really for experimental use. So we have the other version, the major revision, or the Linux 2.0. So it was released in June 1996. So 2.0 added two major new capabilities, which is support for multiple architectures, including a fully 64-bit native alpha port. So alpha port is patched to the Linux kernel, and then it also support for multiprocessor architecture. So as early as 1996. So they have already this 64-bit port and multiprocessor architectures. So other new features are included, such as improved memory management code, improved TCP/IP performance, support for internal kernel threads for handling dependencies between loadable modules, and for automatic loading of modules on demand. And we have standardized configuration interface. So available for Motorola 68000 series processors, SunSpark systems, and for PC and Power Mac systems. So Linux can run on any PC hardware. Then next is we have the versions 2.4 and 2.6, increased SMP support, which is symmetric multiprocessor, added journaling file system, preemptive kernel, and 64-bit memory support. So the version 3 is released in 2011, so after 5 years, the 20th anniversary of Linux, improved virtualization support, new page write-back facility, improved memory management, and new completely fair scheduler. So next is we have the Linux system. So Linux uses many tools developed as part of Berkeley's BSD operating system, the MIT's X Windows system, and the Free Software Foundation's GNU project. So GNU actually has two meanings. So for those who developed the GNU project, it is called as GNU's or GNU's not Unix. So it's GNU. Actually, its logo is a GNU. It's an of course, it's an animal. So it looks like a buffalo, but because that's also their name, so they make it already as their logo. For them, for those who made this GNU project, they're thinking of a catchy name for their operating system. So that's why GNU or GNU is called GNU's or GNU's not Unix. Since of course it is based on Linux, but they want to separate the GNU from Unix. And then the main system libraries were started by the GNU project with improvements provided by the Linux community. Then Linux networking administration tools were derived from 4.3 BSD code, and then recent BSD derivatives such as FreeBSD have borrowed code from Linux in return. The Linux system is maintained by a loose network of developers collaborating over the internet, with a small number of public FTP sites acting as a de facto standard repositories. Then we have this file system hierarchy standard document maintained by the Linux community to ensure compatibility across the various system components. So this standard also specifies overall layout of a standard Linux file system, determines under which directory names configuration files, libraries, system binaries, and runtime data files should be restored. Since Linux is an open source operating system, so it's a non-profit. So mostly the members of the community, of the Linux community, they really are maintaining repositories for Linux. So that's how the Linux community works. Okay, we have the Linux distributions, or as I've said, informal flavors. So standard precompiled set of packages or distributions include the basic Linux system, system installation and management utilities, and ready to install packages of common Unix tools. The first distributions manage these packages by simply providing a means of unpacking all the files into the appropriate places. Modern distributions include advanced package management. Actually, for Linux distributions, most of them have, I encountered with regards to Linux flavors or distributions, they have this live CD mode. Live CD, for example, you are not sure if you really want this type of distribution of Linux, then they have an option to view it or preview it by using the live CD. Of course, live CD is very slow because the operating system is run from the optical disk. That's only for preview, so that if you appreciate or you like the interface of that particular Linux distribution, and then inside that live CD interface, actually for live CD it's just a normal computer that you're going to boot, but then again, it is relatively slower than it is installed because it is working, it's reading in a optical disk, so it's a bit slower. But if you really decided that it is already the right operating system for you, Linux variant, then inside that live CD is you can install. So you don't need to restart again to install. No, there is already a link in which or icon that you can click, so that you can undergo the proper installation of the Linux operating system that you have chosen. So early distributions included SLS and Slackware. So SLS is soft landing Linux system. I'm not familiar with the Linux distribution because I think Linux distribution has, I think it's more than, definitely it's more than 100 because of the power, because it's open source. Anyone can create your own operating system based on Linux. And then Slackware is another Linux distribution. So Red Hat and Debian are popular distributions from commercial and non-commercial sources, respectively, and others include Canonical and SUSE. So Debian, actually, it is where the Mac OS operating system or Mac OS is based on, from the Debian Linux distribution. So we have the RPM package. So RPM is Red Hat Package Manager. It is the RPM package file format permits compatibility among the various Linux distributions. Though they have this different distributions of Linux, but still, because of RPM package file format, there is still a compatibility between the different Linux distributions. Okay, next is we have Linux licensing. The Linux kernel is distributed under the GNU General Public License, or GPL, the terms of which are set out by the Free Software Foundation, not public domain, because the author did not waive all of their rights. So that's the definition of public domain. In that, not all rights are waived by the author. So if it's public domain, it is already free to use. So examples of, I just have a little discussion with public domain for you to understand. So public domain examples are fairy tales. So for example, Beauty and the Beast, Little Mermaid. Since the authors have already died a long time ago, these fairy tales have already been put to public domain. So there's this very popular animation company in which they animated these public domain fairy tale stories. And then what happens is that, of course, you are free to use that material. But since they animated it, and then they also copyrighted it, which is actually unfair because they got this the story free because it's from the public domain, and then they copyright it. It means that they are they're raking millions or money for that public domain. And then as you can see later on, this animation company have changed their style because um, it's really very unfair. So if they are making stories that are based on fairy tales, but the title of the animation movie is instead of the original public domain title of the story, they change it so that, of course, there will be no dispute with copyright. So that's the idea here with public domain. So public domain is free to use. So as much as possible, no, you should not profit if you are using a public domain document because it is free to use by anyone. So much for public domain. So anyone using Linux or creating their own derivative of Linux may not make the derived product proprietary. Software released under the GPL may not be redistributed as a binary-only product. Actually, for Linux, they can sell their distributions, but must offer the source code too. So that's always their um, agreement that it's a free software, but then they should share the source code for their Linux distribution, even if it's can be sold. Okay, next is we have the design principles. So Linux is a multi-user, multitasking system with a full set of Unix compatible tools. Its file system adheres to traditional Unix semantics, and it fully implements the standard Unix networking model. Main design goals are speed. Actually, if because I also used Linux for a long time, for me, Linux with regards to speed, it's still faster than Windows. And then efficiency, as I've said, when I try to terminate a program, abnormally terminate or abort it, it's as fast. It really reacts fast. While for Windows, it is really very slow. And then we also have standardization. So Linux is designed to be compliant with the relevant POSIX documents. At least two Linux distributions have achieved official POSIX certification. It also supports pthreads and a subset of POSIX real-time process control. So the Linux programming interface adheres to the SVR4. So SVR4 is System 5. For the V it is read as 5, released for Unix semantics rather than to BSD behavior. So these are the components of a Linux system. So we have loadable kernel modules, and then the Linux kernel, and then the system shared libraries. And then there is a division between system management programs, user processes, user utility programs, and compilers. So in addition to the discussion of a Linux components of a Linux system, so like most Unix implementations, Linux is composed of three main bodies of code. The most important distinction between kernel and all other components. So the kernel is responsible for maintaining the important abstractions of the operating system. The kernel code executes in kernel mode, of course, with full access to all the physical resources of the computer. And then all kernel code and data structures are kept in the same single address space. So the system libraries define a standard set of functions through which applications interact with the kernel and which implement much of the operating system functionality that does not need the full privileges of kernel code. And then the system utilities perform individual specialized management tasks. And then user mode programs, rich and varied. They can have a graphical user interface, or it can be in multiple shells like the born again. It's a terminal. Multiple shell meaning it's the command line interpreter in relation to Windows. And then this bash is used for if you remembered my discussion, for you to be an administrator, so you need the command sudo and then bash. and then it will and by that command you are already the root, you're already in the root and you are the administrator, and you can do whatever you want to modify within the system. So next is we have the kernel modules. So sections of kernel code that can be compiled, loaded, and unloaded independent of the rest of the kernel. A kernel module may typically implement a device driver, a file system, or a networking protocol. The module interface allows third parties to write and distribute, on their own terms, device driver or file systems that could not be distributed under the GPL. Then the kernel modules also allow a Linux system to be set up with a standard, minimal kernel without any extra device drivers built on it. So the four components to Linux module support are, we have the module management system, we have the module loader and unloader, the driver registration system, and the conflict resolution mechanism. This will be discussed later in the slides. So first is we have the module management. It supports loading modules into memory and letting them talk to the rest of the kernel. So module loading is split into two separate sections, which is the first section is managing sections of module code in kernel memory, and the other section is handling symbols that modules are allowed to reference. So the module requester manages loading requested but currently unloaded modules. It also regularly queries the kernel to see whether the dynamically loaded module is still in use, and will unload it when it is no longer actively needed. So for driver registration, so it allows modules to tell the rest of the kernel that a new driver has become available. The kernel maintains dynamic tables of all known drivers and provides a set of routines to allow drivers to be added to or removed from these tables at any time. So registration tables include the following items, such as the device drivers, file systems, network protocols, and the binary format. So for conflict resolution, so conflict resolution is a mechanism that allows different device drivers to reserve hardware resources and to protect those resources from accidental use by another driver. So the conflict resolution module aims to, first is prevent modules from clashing over access to hardware resources. It prevents autoprobes from interfering with existing device drivers. So autoprobe is a device driver probe that auto-detects device configuration. Then another objective of conflict resolution module is resolve conflicts with multiple drivers trying to access the same hardware, such as kernel maintains list of allocated hardware resources, driver reserves resources with kernel database first, and reservation request rejected if resource is not available. So next is we have the process management. So Unix process management separates the creation of processes and the running of a new program into two distinct operations. So actually Linux is just the same with Unix in relation to process management. So as you can remember, the fork system call creates a new process, and then a new program is run after a call to exec or execute function or system call. Under Unix, a process encompasses all the information that the operating system must maintain to track the context of a single execution of a single program. And on the other hand, under Linux, process properties fall into three groups: the process's identity, the environment, and the context. So first is we have process identity. So the process ID or the PID, it is a unique identifier for the process. It is used to specify processes to the operating system when an application makes a system call to signal, modify, or wait for another process. And the next is we have the credentials. So each process must have an associated user ID and one or more group IDs that determine the process's rights to access system resources and files. So for credential, so the process must have a user ID and then a group ID. Then next is we have personality, though these are not really people, but for process identity, they have this personality. So not traditionally found on Unix systems, but under Linux, each process has an associated personality identifier that can slightly modify the semantics of certain system calls. So this scheme is used primarily by emulation libraries to request that system calls be compatible with certain specific flavors of Unix. And then aside from that is we also have the namespace. It is the specific view of the file system hierarchy. So most processes share common namespace and operate on a shared file system hierarchy. But each can have unique file system hierarchy with its root directory and set of mounted file systems. So next is we have the process environment. So the process's environment is inherited from its parent, and it is composed of two null terminated vectors such as the first, the argument vector, lists the command line arguments used to invoke the running program, conventionally starts with the name of the program itself, and then the other vector is we have the environment vector. It is a list of name is equal to value pairs that associates named environment variables with arbitrary textual values. So passing environment variables among processes and inheriting variables by a process's children are flexible means of passing information to components of the user mode system software. And then the environment variable mechanism provides a customization of the operating system that can be set on a per process basis rather than being configured for the system as a whole. Okay, next is we have the process context. So the constantly changing state of a running program at any point in time. So the scheduling context is the most important part of the process context because it is the information that the scheduler needs to suspend and restart the process. So the kernel maintains an accounting information about the resources currently being consumed by each process and the total resources consumed by the process in its lifetime so far. And then the file table is an array of pointers to kernel file structures. So when making file I/O system calls, processes refer to files by their index into this table, the file descriptor or the FD. So whereas the file table lists the existing open files, the file system context applies to requests to open new files. So the current root and default directories to be used for new file searches are stored here. And then we also have the signal handler table defines the routine in the process's address space to be called when specific signals arrive. And we also have the virtual memory context of a process that describes the full contents of its private address space. So next is we have processes and threads. So Linux uses the same internal representation for processes and threads. A thread is simply a new process that happens to share the same address space as its parent. Both are called tasks by Linux, processes and threads. A distinction is only made when a new thread is created by the clone system call. So fork creates a new task with its own entirely new task content. Then the clone creates a new task with its own identity, but that is allowed to share the data structure of its parent. So using clone gives an application fine-grained control over exactly what is shared between two threads. So we have an example here for flags. So clone underscore fs, it is the file system information is shared. Clone underscore vm, the same memory space is shared. Clone underscore sighand, handlers are shared. And then clone underscore files, the set of open files is shared. So next is we have the scheduling. So the job of allocating CPU time to different tasks within the operating system. So that is scheduling. While scheduling is normally thought of as the running and interrupting of processes, in Linux, scheduling also includes the running of the various kernel tasks. So it's not just with the jobs in relation to processes, but also to various kernel tasks. So running kernel tasks encompasses both tasks that are requested by a running process and tasks that executes internally on behalf of a device driver. So as of the version of Linux 2.5, new scheduling algorithm, which is preemptive priority based known as the runtime big O notation, big O function of 1. So it means it is constant. So it's a real-time range and has a nice value, and then had challenges with interactive performance. So by Linux version 2.6 and higher, it was a completely fair scheduler or CFS is introduced. Actually, it is already discussed in the previous chapters. So CFS again is eliminates traditional common idea of time slice. Instead, all tasks are allocated portion of processor's time, and then CFS calculates how long a process should run as a function of total number of tasks. So it's depends upon the proportion. And then n runnable tasks means each gets 1 over n of the processor's time. Then weights each task with its nice value. So smaller nice value, the higher the weight, and of course, the higher the priority. So then each task run with for time proportional to task's weight divided by total weight of all runnable tasks. So configurable variable target latency is desired interval during with each task should run at least once. So consider simple case of two runnable tasks with equal weight and target latency of 10 milliseconds. Each then runs for 5 milliseconds. So 10 milliseconds divided by 2. If 10 runnable tasks, each runs for 1 milliseconds because 10 divided by 10 is equal to 1. And then we have the minimum granularity ensures each run has reasonable amount of time for which actually violates the fairness idea. So next is we have the kernel synchronization. So a request for kernel mode execution can occur in two ways. First is a running program may request an operating system service either explicitly via a system call or implicitly, for example, when a page fault occurs. Another way is a device driver may deliver a hardware interrupt that causes the CPU to start executing a kernel-defined handler for that interrupt. So kernel synchronization requires a framework that will allow the kernel's critical sections to run without interruption by another critical section. So Linux uses two techniques to protect critical sections. So normal kernel code is non-preemptible. So it cannot be interrupted until 2.6 version of Linux. When a time interrupt is received while a process is executing a kernel system service routine, the kernel's need underscore resched flag is set so that the scheduler will run once the system call has completed and control is about to be returned to user mode. So it means that you really cannot interrupt if the process is executing a kernel system service routine. And then the second technique applies to critical sections that occur in an interrupt service routine. So by using the processor's interrupt control hardware to disable interrupts during a critical section, the kernel guarantees that it can proceed without the risk of concurrent access of shared data structures. By this second technique, it also provides spin locks, semaphores, and reader and writer versions of both. Behavior modified if on single processor or multi. So for single processor, it's either disable kernel preemption and enable kernel preemption. And then for multiple processor, acquire spin lock and release spin lock. So to avoid performance penalties, Linux kernel uses a synchronization architecture that allows long critical sections to run without having interrupts disabled for the critical section's entire duration. So interrupt service routines are separated into a top half and a bottom half. So the top half is a normal interrupt service routine and runs with recursive interrupts disabled, while the bottom half is run with all interrupts enabled by a miniature scheduler that ensures that bottom halves never interrupt themselves. So this architecture is completed by a mechanism for disabling selective bottom halves while executing normal foreground kernel code. So next is we have the interrupt protection levels. So each level may be interrupted by code running at a higher level, but will never be interrupted by code running at the same or a lower level. So user processors can always be preempted by another process when a time sharing scheduling interrupt occurs. So top half is interrupt handlers. It is has the highest priority, and the user mode programs this has the lowest priority. For example, a user program is running and then there is a top half interrupt handler. So what the Linux system will do is that this will be preempted. So this will be in a pause for execution, and it will deal first with the top half interrupt handler. So that's why user mode programs here and kernel system service routines are with a note here preemptible, meaning they can really be at a pause, or they will be switched if top half interrupt handlers or bottom half interrupt handlers will be available for execution. So next is we have symmetric multiprocessing. So Linux 2.0 was the first Linux kernel to support the symmetric multiprocessing hardware. Separate processes or threads can execute in parallel on separate processors. Then until version 2.2, to preserve the kernel's non-preemptible synchronization requirements, SMP imposes the restriction via a single kernel spin lock that only one processor at a time may execute the kernel mode code. And then the later releases of Linux implement more scalability by splitting single spin lock into multiple locks, each protecting a small subset of kernel data structures. And then for version 3, adds even more fine-grained locking, processor affinity, and load balancing. So for memory management, so Linux's physical memory management system deals with allocating and freeing pages, groups of pages, and small blocks of memory. It has additional mechanisms for handling virtual memory, memory mapped into the address space of running processes. So it also splits memory into 4 different zones due to hardware characteristics. So actually, it's architecture specific, for example, on x86. So for zone, underscore DMA, which is the direct memory access, the physical memory should be less than 16 megabyte memory. Then zone underscore normal, it should be from 16 to 896 MB range. While the zone underscore high mem or high memory is greater than 896 megabytes of memory. So managing physical memory. So the page allocator allocates and frees all physical pages. It can allocate ranges of physically contiguous pages on request. So the allocator uses a body heap algorithm to keep track of available physical pages. So what is body heap algorithm? So it is the use of a power of 2 allocator for the kernel heap. So how does it is done? Each allocatable memory region is paired with an adjacent partner. Whenever two allocated partner regions are both freed up, they are combined to form a larger region. If a small memory request cannot be satisfied by allocating an existing small free region, then a larger free region will be subdivided into two partners to satisfy the request. Okay. Next is memory allocations in the Linux kernel occur either statically or drivers reserve a contiguous area of memory during system boot time or dynamically via the page allocator. So it also uses a slab allocator for kernel memory. I've already discussed in the previous chapters the slab allocator. So page cache and virtual memory system also manage physical memory. So page cache is kernel's main cache for files and main mechanism for I/O to block devices. And also page cache stores entire pages of file contents for local and network file I/O. So this is the body heap. So example, we have 4 gig 4 kilobyte of free memory, and then it will be paired here. So for 4 KB, if it is already freed, then this will be they will be joined to form the 8 kilobyte. So that is the body heap. And then if there is an exact pair of 8 kilobyte, if the pair is also 8 kilobytes, then this will be joined and it will become 16 kilobytes. But it is also said here that if a small memory request cannot be satisfied by allocating an existing small free region, then a larger free region will be subdivided into two partners to satisfy the request. So for example, if your request is too small for a 16 MB, only for example 2 MB, then this will be divided into two until it satisfies. Of course, if the request is only two, then how if it will not be divided into two, then you will waste 14 kilobytes. So it will divide it by always by 2 until, for example, you only need 2. So 4 can still be divided into 2 to make it 2 kilobytes. So this is the slab allocator in Linux. Actually, it has already been illustrated in the previous chapters. So we have this kernel objects, an example of 3 kilobyte objects and 7 kilobyte objects. And then from the caches, they are contained here. And then from these caches, it is saved in the slabs. Okay, so these are the physically contiguous pages, and for example, in the hard disk drive. And also, this is the same fashion with the 7 or the 3 kilobyte objects. So it's in the cache, and it will be also copied in the slabs. So next is we have the virtual memory. So the VM system maintains the virtual address space visible to each process. It creates pages of virtual memory on demand and manages the loading of those pages from disk or their swapping back out to disk as required. The VM manager maintains two separate views of a process's address space. First is the logical view describing instructions concerning the layout of the address space. So the address space consists of a set of non-overlapping regions, each representing a continuous page-aligned subset of the address space. The other view is the physical view of each address space, which is stored in the hardware page tables for the process. So virtual memory regions are characterized by the backing store, which describes from where the pages for a region come. Regions are usually backed by a file or by nothing. So by nothing, that is the demand zero memory. Or demand zero memory, it is a virtual memory backed by nothing. When a process tries to read a page in such a region, it is given a page of memory filled with zeros. That's why it's a demand zero memory. So the region's reaction to writes may be page sharing or copy on write. And then another, the kernel creates a new virtual address space for number one, when a process runs a new program with the exec system call, and another is upon creation of a new process by the fork system call. So on executing a new program, the process is given a new, completely empty virtual address space. The program loading routines populate the address space with virtual memory regions. Creating a process with fork system call involves creating a complete copy of the existing process's virtual address space. The kernel copies the parent process's VMA descriptors, then creates a new set of page tables for the child. And then the parent's page tables are copied directly into the child's, with the reference count of each page covered being incremented. And then after the fork, the parent and child share the same physical pages of memory in their address spaces. So for Linux, how about swapping and paging? So the VM paging system relocates pages of memory from physical memory out to disk when the memory is needed for something else. So the VM paging system can be divided into two sections. So the first section is by using the page out policy algorithm, decides which pages to be write out to disk and when. And then another is the paging mechanism actually carries out the transfer and pages data back into physical memory as needed. So for swapping and paging for Linux, can page out to either swap device or normal files. Bitmap is used to track use blocks in swap space kept in physical memory. An allocator uses next fit algorithm to try to write contiguous runs. So if we have virtual memory, we also have the kernel virtual memory. So the Linux kernel reserves a constant, architecture-dependent region of the virtual address space of every process for its own internal use. So this kernel virtual memory area contains two regions. First is the static area that contains page table references to every available physical page of memory in the system so that there is a simple translation from physical to virtual addresses when running kernel code. And then the other region is the remainder of the reserved section is not reserved for any specific purpose. Its page table entries can be modified to point to any other areas of memory. So next is how about executing and loading user programs. So Linux maintains a table of functions for loading programs. It gives each function the opportunity to try loading the given file when an exec system call is made. So the registration of multiple loader routines allows Unix to support both ELF. So ELF is a Unix standard format for relocatable and executable files. And then we have the A.out binary formats. It is a file format used in older versions of Unix-like computer operating systems for executables, object code, and in later systems, shared libraries. So initially, binary file pages are mapped into virtual memory. Only when a program tries to access a given page will a page fault result in that page being loaded into physical memory. And then an ELF format binary file consists of a header followed by several page-aligned sections. So the ELF loader works by reading the header and mapping the sections of the file into separate regions of virtual memory. So this is the memory layout for ELF programs. So we have this forbidden region. There's a region for program text, for initialized data and initialized data. So runtime data, it can increase its size, as you can see here. So and then we have the BRK pointer or the break pointer. And then there is also a section for memory mapped region. So this memory map region can increase and also the stack. And then we have the kernel virtual memory. So it's a memory invisible to user mode code. Okay, next is we have the static and dynamic linking. So a program whose necessarily library functions are embedded directly in the program's executable binary file is statically linked to its libraries. So the main disadvantage of static linkage is that every program generated must contain copies of exactly the same common system library functions, as well as dynamic linking is more efficient in terms of both physical memory and disk space usage because it loads the system libraries into memory only once. So Linux implements dynamic linking in user mode through special linker library. So every dynamically linked program contains a small statically linked function called when process starts. Then next is map the linked library into memory. And then link library determines dynamic libraries required by process and names of variables and functions needed. And then maps libraries into middle of virtual memory and resolves references to symbols contained in the libraries. And then shared libraries compiled to be position independent code or PIC so can be loaded anywhere. So PIC is a binary code compiled from shared libraries that can be loaded anywhere in memory as it is said in the slide. Okay, next, how about the Linux file systems? So to the user, Linux file system appears as a hierarchically directory tree obeying Unix semantics. Internally, the kernel hides implementation details and manages the multiple file systems via an abstraction layer that is the virtual file system or the VFS. So the Linux VFS is designed around object-oriented principles and is composed of four components. So a set of definitions that define what a file object is allowed to look like. So these four components is we have the inode object. Structure represent an individual file, while the file object, it represents an open file, while the super block object represents an entire file system, and the den-tree object represents an individual directory entry. So so as continuation for this one, so it's just the same text with the previous slide. So for example, for the file object operations include from struct file underscore operations in this path. So int open, this system call is open a file, then s size t read, read from a file, s size t write is write to a file, and of course nm map is memory map a file. So next is we have the Linux ext3 or the extended file system version 3. So ext3 is a standard on disk file system for Linux. It uses a mechanism similar to that of the BSD fast file system or FFS for locating data blocks belonging to a specific file. So it oversees extfs and then the ext2 file systems, of course, because this is the newer file system that is used by Linux. Works underway on ext4, adding features like extents, and of course, many other file system choices with Linux distros or distributions. So the main differences between EX2FS and FFS concern their disk allocation policies. So in FFS, the disk is allocated to files in blocks of 8 kilobyte, with blocks being subdivided into fragments of 1 kilobyte to store small files or partially filled blocks at the end of a file. And then ext3 does not use fragments. It performs its allocations in smaller units. So for ext3, the default block size varies as a function of total size of file system with support for 1, 2, 4, 8 kilobyte blocks. So also, ext3 uses cluster allocation policies designed to place logically adjacent blocks of a file into physically adjacent blocks on disk so that it can submit an I/O request for several disk blocks as a single operation on a block group. And then it also maintains a bitmap of free blocks in a block group, searches for free byte to allocate at least 8 blocks at a time. So we have an allocation here of the ext2fs block allocation policies. So for this one, for this, each row represents a sequence of set and unset bits in an allocation bitmap, indicating used and free blocks on disk. So in this case, in this first case, if we can find any free blocks sufficiently near the start of the search, then we allocate them no matter how fragmented they may be. So the fragmentation is partially compensated for the fact that the blocks are close together and can probably be read without any disk 6. So furthermore, allocating them all to one file is better in the long run than allocating isolated blocks to separate files once large free areas become scarce on disk. So this legend here is block selected by the allocator. So on the second case, which is this is the one. So we have not immediately found a free block close by. So we search forward for an entire free byte. So it searched for a free block. Okay. So in the bitmap, so if we allocated that byte as a whole, we would end up creating a fragmented area of free space between it and the allocation preceding it. Thus, before allocating, we back up to make this allocation flush with the allocation preceding it. And then we allocate forward to satisfy the default allocation of 8 blocks. Okay, next is we have journaling. So ext3 implements journaling. So with file system updates first written to a log file, it's like a file system that has a journal. So that's why it's called journaling in the form of transactions. So once in a log file, considered committed, and then over time, log file transactions replayed over file system to put changes in place. So on system crash, some transactions might be in journal but not yet placed into the file system, so must be completed once system recovers, and no other consistency checking is needed after a crash. So it's much faster than the older methods. It improves write performance on hard disk by turning random I/O into sequential I/O. So next is we have the Linux Proc file system. So the Proc file system does not store data. Rather, its contents are computed on demand according to user file I/O request. So Proc must implement a directory structure and the file contents within. It must then define a unique and persistent inode number for each directory and files it contains. So it uses this inode number to identify just what operation is required when a user tries to read from a particular file inode or perform a lookup in a particular directory inode. When data is read from one of these files, Proc collects the appropriate information, formats it into text form, and places it into the requesting process's read buffer. So for input and output, so the Linux device-oriented file system accesses disk storage through two caches. So first is the data is cached in the page cache, which is unified with the virtual memory system. And then another one is metadata is cached in the buffer cache, a separate cache indexed by the physical disk block. So Linux split all devices into three classes, which is the block devices, allow random access to completely independent fixed size of blocks of data. So example of block devices, of course, are hard disk drives, and that's the best example. And then character devices include most other devices. They don't need to support the functionality of regular files. So character devices, example is a keyboard, and the network devices are interfaced via the kernel's networking subsystem. So network devices, of course, are devices that have something to do with communications and network. For example, modem or your router. Okay, first is we have the block devices. Provide the main interface to all disk devices in a system. So the block buffer cache serves two main purposes. First is it acts as a pool of buffers for active I/O, and it also serves as a cache for completed I/O. So the request manager manages the reading and writing of buffer contents to and from a block device driver. So kernel 2.6 version of Linux introduced the completely fair queuing or the CFQ. So now it is the default scheduler, fundamentally different from elevator algorithms. It also maintains a set of lists, one for each process by default, and it also uses C-scan algorithm with round robin between all outstanding I/O from all processes. As you can remember, elevator algorithm is the scan algorithm. And then 4 blocks from each process put on at once. So this is the device driver block structure. So we have this for the block devices, for the character devices, and the network devices. And then this interface here, the TTY driver or the teletype driver, and then we have the line discipline will be discussed on the next slides. Okay, next is we have the character devices. So a device driver which does not offer random access to fixed blocks of data. A character device driver must register a fixed set of functions rather, which implement the driver's various file I/O operations. So the kernel performs almost no pre-processing of a file read or write request to a character device, but simply passes on the request to the device. So the main exception to this rule is that the special subset of character device drivers which implement terminal devices for which the kernel maintains a standard interface. So we have the line discipline, as you can see with the structure. As you can see here, this is the line discipline for the structure of the device driver block. Okay, it is an interpreter for the information from the terminal device. So again, character devices, an example is keyboard. So the most common line discipline is the TTY discipline. So literally means TTY is teletype. So TTY discipline, which glues the terminal's data stream onto standard input and output streams of users running processes, allowing processes to communicate directly with the user's terminal. So several processes may be running simultaneously. The TTY line discipline responsible for attaching and detaching terminals input and output from various processes connected to it as processes are suspended or awakened by the user. So other line disciplines also are implemented, have nothing to do with the I/O to user process, such as the PPP. PPP is point-to-point protocol or the SLIP networking protocol. So SLIP is Serial Line Internet Protocol. So next, how about the interprocess communication in Linux? So like Unix, Linux informs processes that an event has occurred via signals. So there is a limited number of signals and they cannot carry information. Only the fact that a signal occurred is available to a process. So the Linux kernel does not use signals to communicate with processes with are running in kernel mode. Rather, communication within the kernel is accomplished via scheduling states and wait underscore queue structures. So it also implements the System 5 Unix semaphores such as process can wait for a signal or a semaphore. Semaphores are scale better and operations on multiple semaphores can be atomic. Okay, next is passing data between processes. So the pipe mechanism allows a child process to inherit a communication channel to its parent. Data written to one end of the pipe can be read at the other end. So, shared memory offers an extremely fast way of communicating. Any data written by one process to a shared memory region can be read immediately by any other processes that has mapped that region into its address space. So, to obtain synchronization, however, shared memory must be used in conjunction with another inter-process communication mechanism. So next is the network structure. So networking is a key area of functionality for Linux because it supports the standard internet protocols for Unix to Unix communications. It also implements protocols native to non-Unix operating systems, in particular protocols used on PC networks such as Apple Talk. So Apple Talk, it is already discontinued by Apple. And then we have the IPX, the Inter-Network Packet Exchange. So internally, networking in the Linux kernel is implemented by three layers of software. We have the socket interface, the protocol drivers, and the network device drivers, as you can see with the illustration of the device driver block structure. So most important set of protocols in the Linux networking system is the Internet Protocol Suite. It implements routing between different hosts anywhere on the network. On top of the routing protocol are built the UDP or the User Datagram Protocol, TCP or the Transmission Control Protocol, and the ICMP, which is the Internet Control Message Protocol. Then packets also pass to firewall management for filtering based on firewall chains of rules. So firewall chains, these are ordered list of rules that specifies one of a number of possible firewall decision functions plus matching components. It is a configuration of the firewall rules. So next is security for Linux. So the pluggable authentication modules or PAM system is available under Linux. So PAM or PAM is based on a shared library that can be used by any system component that needs to authenticate users. Access control under Unix systems, including Linux, is performed through the use of unique numeric identifier. We have the user ID and the group ID. Then access control is performed by assigning objects a protection mask, which specify which access mode, may it be read, write, or execute, or all, or both, or none at all, are to be granted to processes with owner, group, or world access. So Linux augments the standard Unix set UID mechanisms in two ways, or set user ID. First way is it implements the POSIX specification saved user ID mechanism, which allows a process to repeatedly drop and reacquire its effective user ID or the UID. And then the other way, it has added process characteristic that grants just a subset of the rights of the effective UID. And then Linux provides another mechanism that allows a client to selectively pass access to a single file to some server process without granting it any other privileges. So this is the end for this discussion. So I hope that you'd learn something all about the Linux system, the different implementation of its operating system, specifically for all the concepts or aspects of the operating system. So for our next lesson, we'll be having a case study all about Windows. So if again, please do not forget to subscribe to my YouTube channel. So thank you very much Good day and stay safe.